Okay, in this video we're going to look at some example problems at the end of chapter 4 that I didn't get a chance to look at with you. And those examples all involve column buckling. And so the first example, and we've already covered the Euler equations, says let's use those Euler equations, and instead of using them in a form where we can do some checking, let's instead use them in a form where we can do design. And in doing design, if we're going to choose a round cross section, design means find the diameter, which causes the stresses to go right up to our limit. If we're going to design for a rectangular cross section has two numbers, and so we need to choose a width and a height of the cross section. The equation is only one equation. It's not going to give us both, so we'll set it up so that we pick one of the numbers, and it'll give us the other value in the cross section. And then we can try lots of different guesses and choose lots of different cross sections. Okay. So in order to fulfill this problem, we need to first go back to the checking form of the equation, which is several pages back, and I'm scrolling back to it, and it is right here. It says our P critical over area is equal to our N fixity. It involves E and it involves L over K squared. Area for a circle is going to involve the diameter, of course. Remembering that K is related to moment of inertia, right here. K is related to moment of inertia and area. So we could solve for K for a rectangle in terms of diameter. When we do that and plug that in here and solve for diameter, we'll have a design equation. Let's look at how that was done then down in the problem. Getting back to the problem statement. So we're going to use the Euler equation, 4-44. We'll write area as pi d squared over 4, and K is the square root of I over area, and I is pi d to the 4th over 64, and area is pi d squared over 4 again. Take the square root of all of that. Notice that K for a circle is a fairly simple thing. K is just diameter over 4. Plugging in that K equal diameter over a 4, and that area equal pi d squared over 4, and having P critical moved to the other side, plug it in and solve for diameter is equal to this. If we're told that we want to size a column and choose its diameter to support a certain critical pressure at a certain length using a certain modulus and certain N fixity, here's our equation. If we want to do the same thing with a rectangular column, we're going to have to replace I in terms of B and H. We'll have to replace area in terms of B and H. We can find K in terms of IA, which is in terms of B and H, and here is our K squared value, and substituting all of those into equation 4-44. And here we're making an assumption that H is less than B, H is the small number, and that we know H and we wish to solve for B. So we'll take this equation and rearrange it as if we know H and plan to solve for B. Now for a rectangular shape and we're going to buckle, we're more likely to buckle in the skinny direction, and the skinny direction buckling would have the small distance H in the H cubed part of the moment of inertia. And so this would be a correct equation for buckling in the skinny direction, okay, or buckling in the direction which H goes into the H cubed moment of inertia term.